All right, let's say we have a ramp, and on that ramp there's a cart which is attached by a pulley to a mast hanging off the edge. And the ramp rises at some angle theta. And we'll call the cart mass 1 and the mass on the edge mass 2. And we want to know what's the acceleration and what is the tension. Well, since we want acceleration, we're going to start with Newton's second law. Some of the forces on object 1 is mass 1 times its acceleration. And since both of the objects are tied together, then they're going to have the same acceleration throughout the motion. So we look at the forces on mass 1. We have normal force, we'll have tension, and we have gravity. And the acceleration, I'm going to pick it to be down the ramp. I'm going to say that force is going to be winning, and it's going to go down the ramp. So I want to tilt that so that I can get the acceleration in the x-axis. Now the angle down there is theta. That's what matches the ramp, which means that angle is 90 minus theta. So that angle is 90 minus theta. So now we have to look at each force and determine if it's in the x. We have to determine if that force is helping, it'll be a positive force, or is it hurting the motion, it'll be a negative force. And then we have to determine, is it all in the x? If it's not all in the x, then we must use the cosine of the reference angle to find out how much of that force is actually in the x direction. The reference angle is the angle between the force and the x-axis. So in this case, that's the 90 minus theta. So we have gravity. Is it in the x? Yep, it's helping. And the angle is 90 minus theta because it's not all in the x. Now we look at tension. Is it in the x? Yes. Is it helping or hurting? Tension's hurting the motion of that. So we have a negative sign. Is it all in the x? Yes, it's all in the x, so I don't have to worry about anything. The normal force. Is it in the x? Nope. So we don't even need to use it. And that equals mass 1 times acceleration. Now let's take a look at this triangle here. We have theta and we have 90 minus theta. Cosine 90 minus theta is adjacent over hypotenuse, but that would be the same as sine theta opposite over hypotenuse. So we have g sine theta minus tension equals m1a. Now let's look at mass 2. Some of the forces on mass 2 is acceleration. And what forces are on mass 2? We got tension pulling it up and gravity pulling it down. So we have tensions in the x. Is it helping or hurting? Since we said that it's going to go, mass 2 is going down the ramp, mass 1 is going up, so tension's helping, it'll be positive. Gravity is hurting, so it's negative. So we'll clear all this out so we have room to work. Remember, the gravity is a force, which is equal to the mass times the acceleration due to gravity. So we can substitute that into each of these equations. So now we have tension equals m2g equals m2a. And we have m1g. And then that's times sine theta minus tension equals m1a. And now I have two equations with two unknowns that I'm looking for, tension and acceleration. So I move that second equation over. And what I'm going to do is I'm going to add these two equations together because using elimination method, then I can get rid of tension. So that gives me m1g sine theta minus m2g equals m1a plus m2a. I'm just going to factor out g on the left-hand side and factor out a on the right-hand side. And then I just divide both sides by m1 plus m2, and I get my answer for the acceleration. If this ends up being negative once you put your mass values in and your angle, then that means we just picked the wrong way, and that means that the cart will go up the ramp and the mass will fall down. So if we look at this, you can also take a look and say, what would happen if mass 1 is 0, meaning there's no mass on the end? Well, if you look, the mass 1 terms will cancel out, and we'll have minus m2 over m2, which is just minus 1, and we would get acceleration as minus g, and that would make sense for that. And then lastly, if we wanted to get the tension for this, we could go back up, substitute into one of the equations, and solve for tension.